Part C.2, Fibonacci numbers. It is a very famous problem, Fibonacci numbers. So a lot of interesting properties for this kind of special numbers. In this section, we will use this example first. This example is relatively simple, but there are many interesting things we can learn. So it is pretty good example. Our problem 11, calculate Fibonacci numbers. Given recursion formula, initial values f0, f1 given. After that, we have recursion formula. Recursion formula very simple. Fn equals Fn minus 1 plus Fn minus 2. Question. Find Fibonacci number Fn for any given positive integer n. That's the problem. Okay? First, if we just do experiments, we can easily get a sequence of Fibonacci numbers. All right. Next, in order to find Fibonacci number Fn for any given integer, what is the fastest algorithm? Right? What is the fastest algorithm? All right, So here, plan. Look at our plan. First, we solve it algorithmically. We need to derive an algorithm to find it. First way, we try it. Then we need to write a computer program to implement, some ways, different ideas. We may have several ideas, so we try to implement different ways calculating the Fibonacci numbers. But another also very important way, solve it mathematically, and we need to derive math formula. That is not easy. We need to do a lot of work. All right. Here, look at the first implementation. Given recursion formula, we have enough information so we can implement Fibonacci number calculation function using recursive algorithm, right? Recursion formula, recursive algorithm, it looks very natural. So we just do it directly, or brute force. Here, we use the brute force method. All right, here, this is the code. Code also, you can see, pretty straightforward. First base case, second base case. After you pass those two base cases, then the main case, recursion call. That's it. Return the formula you need to get f of n, or Fibo of n. But this is a recursion call. We know the programming language takes care of the whole thing in the recursion call. So we don't worry about it. All right, we get a simple solution, right? It's our first simple solution. Then discussion, a question. All right. No problem. We get correct answer. This function returns the correct function value. But the question is, efficiency issue. Do we have a good efficiency for this algorithm? Is it a good implementation? Are we satisfied with this implementation? Right? Yeah. Unfortunately, the answer is it is a horrible. Yeah. So why I use this horrible? Because it's not just little bad, it is really, really bad. Really, really bad. So that's why, yeah, hard to use a very precise word to describe it. Just, horrible. Don't even try it. Yeah. Too slow. Very, very slow. Later, we may have a chance to do experiments. Yeah. So I'm trying to give you project number 2. Project number 2. So let you get a hands-on experience how bad it is. Okay. Yeah. In our second project, we need to compare efficiency of 2 different algorithms. 2 different algorithms. Yeah. Okay. Yeah. Probably more than 2. Yeah. Probably more than 2. 3. Yeah. So I'm thinking about, probably 3 algorithms. Yeah. Calculating Fibonacci numbers. So I will give you those 3, the detail of those 3 algorithms. Then you write the programs to compare their efficiencies. Yeah. How bad is the algorithm? Very bad, but we need to know why it is bad, right? After that, can we improve it? Yes, we can. We have a lot of different ideas to improve the algorithms. Yeah. All right. Here, first I want to explain why it is so bad. Yeah. I just use one simple diagram to show you it is bad. Yeah. Here I draw a recursion tree to visually explain the reason it is so bad. Okay, all right. I just show you how do we calculate fiber of 6 recursively when we use our previous recursive function called behind the scene. If we can see all the details in implementation, what is the big amount of job behind the scene. We need to see that. All right, so let's look at that. You need to find fiber of 5, fiber of 4 before you can get a value fiber of 6. Similarly, we need to go down, right? To get fiber of 5, you need to get fiber of 4, fiber of 3, and so on. So we keep, expand our recursion tree from root to leaves, right? Yeah. So we grow our tree to the pretty big tree. So you can see, in order to calculate just the one fiber numbers, you need to do so many calculations. Okay, yeah, that's a lot of calculation. But that is just for n equals 6. Can you think about when n equals 1 million? How big is that recursion tree? How big? It's very hard to imagine how big it is, but it is huge. You don't want to draw that tree, right? Nobody wants to draw that tree. And nobody wants to calculate Fibonacci number in that way. Okay? Here, in this simple example, you can see it is not efficient. The main reason it is not efficient is we have a lot of redundant calculation. Look at this fiber of 2. How many times we calculate fiber of 2? Here, in this small example, you can see we calculate fiber of 2 5 times, right? 5 times. In this small, relatively small recursion tree, we need to calculate the same number 5 times. Why you need to calculate the same number 5 times, right? Can you calculate fiber of 2 only once, right? In other words, when you have a 1 million problem size, 1 million, how many times you need to calculate one particular smaller Fibonacci number? How many times? All right, so you get the main reason. Too much redundant calculation. The improvement idea is pretty simple. Improvement idea, we just avoid redundant calculation. If you can avoid it, if you can make sure each fiber number, intermediate fiber number, you only need to calculate once, then you should get a pretty good algorithm. Yeah. So with this in your mind, then we have, here I just give you 2 different ways to avoid redundancy. Yeah. The first way, pretty simple, straightforward way, but this time we use iterative algorithm. We do not use recursive algorithm, iterative algorithm. When we use iterative algorithm, we can avoid that redundancy easily. Now, example, to write the code, we calculate F array, right? F array value. First element, second element in the array. After that, we use a for loop. In the for loop, we calculate current fiber number by the sum of previous 2 fiber numbers. No redundant calculation, right? Each fiber number you only need to calculate once. This simple implementation avoids redundancy easily. Okay? All right, so it is a much better algorithm than the previous one. But here, do not jump in that conclusion quickly. So what kind of conclusion? It looks like iterative algorithm easily beats recursive algorithm. Don't jump to that conclusion quickly. For this particular example, for this particular way implementation, that is the case, but we can also use recursive algorithm to avoid redundancy. We can also do, but we implement recursive algorithm carefully. We can still avoid it. The reason is, I do not want to give you the impression recursive algorithm is not a good idea, so we should not use recursive algorithm. That will be very dangerous. Okay? Because it is so powerful. We saw it before, its power. We don't want to throw it away. Right? We don't want to throw away recursive algorithm. So we want to keep it. That is a powerful tool we want to, put in our toolbox. Sometimes we need it to solve some tough problem. Okay, all right, here. Method number 2, recursive algorithm without redundant computation. Here, we just need to do some preparation. If you do that, you can avoid redundancy. All right, here, how to do the preparation. Use an array to store calculated values. Yeah. We need to use array calculated value. Okay? Yeah. When you find one Fibonacci number, store it in the array, and the second time you need to use the same Fibonacci number. Don't calculate it another time, just retrieve it from the array. That's it. That simple idea, you can avoid redundancy in a recursive algorithm. How simple it is, right? Pretty smart way to avoid redundancy. Yeah. So let's look at the next step. Make sure no value is calculated more than once. Yeah, you need to find a way to check it. When you are given a positive integer, can you check if the Fibonacci number corresponds to this positive number is calculated or not? You just do that check. That check should be very fast. Then you make your decision after that. All right? Yeah. Now let's do the implementation details. Yeah. Fibo of n, we store it in f of n array. Okay? Yeah. Yeah. Actually, here the method we used here, it is a very important topic. Yeah. All right. So I will give you comments after we complete this implementation. All right. So the array, in order to make you get a better understanding for this f of n, we use known f array. Yeah. We carefully choose the name for this array, so you can see the value stored in this array elements will tell us if the Fibonacci numbers are known or not. Known array, known f. Okay, yeah. Now we modify our original recursive algorithm, but we put one more step, checking if the current Fibonacci number is known or not. That simple step. All right, let's start. All right. At the beginning, before we started, we create that known f array. At the beginning, we initialize it to equal to 0. All elements we initialize their values to 0 at the beginning. Okay? That is important because later, when we store a Fibonacci number in one location, it's not 0 anymore. So then we just check if the value in I position, I index, is positive or not. If it's positive, the value is known. Don't calculate it another time. Just return the known value. Yeah. So this step. So we add one proof step. Yeah. We do some proof work. Yeah. This proof step. Yeah. All right. After that, then we'll find. We just our original recursive algorithm, right? Yeah. So then, when you return the value, return the known fs. Yeah. So the s, after you find it, you store it in the known array, then you return it. You store it. Before you return it, to store it first, then return it. In that way, you're fine. You can see, in that way, you carefully avoid redundancy. Then, as a result, your algorithm becomes very fast. The no algorithm, before you do some, little things to, detect if the Fibonacci number is known or not. Before you do that, extremely slow. Okay, very, very slow. All right, yeah. All right, a few comments. Yeah, this method, this smart method, there is a very important technique called dynamic programming. That's dynamic programming idea. Yeah. So that's the topic of chapter 8. Of chapter 8. Yeah. For this semester, although I have a plan, so if it's possible, I may cover a little bit dynamic plan. But right now, it looks like it's hard. We don't have much time this semester. So we do not have a lot of chance to learn this important topic. But in this example, you see the first view of dynamic programming. What's the meaning of dynamic programming? The idea is very simple. No repeated calculation. Do some bookkeeping work. Bookkeeping, yeah, here. So what we actually do is bookkeeping. Do some careful bookkeeping work to avoid repeated calculation. That's the essence of dynamic programming. Okay. All right. So let me stop here.